Now let us compare this case with the evacuated tube collector case. Okay. Now evacuated tube collectors will also follow this expression. Okay. For evacuated tubes also you have an absorber coating. This absorber coating is transmitting heat to a heat pipe, which we can assume to be at the same temperature as your absorber coating, and then this heat pipe is transmitting this heat to your heat transfer fluid. Okay, so there is a two-step process, but ultimately it's the same kind of a system. Okay. And you will have a thermal resistance and you have a reflectivity. Now, because you have a cylindrical glass tube, your reflectivity from a cylindrical glass tube or a curved glass is greater than a flat glass. Okay, so your reflectivity rho for your evacuated tube collectors are actually higher. Okay, because it's a curved glass surface, so your angle of incidence of your sun will be higher in many places, and so your reflectivity will also be higher. So your rho is in general higher. However, because you have evacuated the space between your absorber coating and the glazing, your resistivity will also be higher, so there will be lesser heat loss. So if you look at these three values, for an evacuated tube collector, the thermal losses will be usually less and the reflection losses will be more. Okay. So in this expression, if you compare a flat plate collector versus an evacuated tube collector, this is your flat plate collector. This is your evacuated tube collector. Your rho 2 is greater than rho 1, higher reflectivity. So 2 is basically evacuated tube, 1 is flat plate. So 1 minus rho 2 is lower, 1 minus rho 1 is higher. Okay, but your resistance, thermal resistance R2 for your evacuated tube collector is greater than R1. So the slope, remember this is your expression here, R2 is greater, so the slope is lower. So your slope for your evacuated tube collector is much less steep than your flat plate collector. So now if you compare these two together, there will be a crossover point. At delta T values below this delta T1 value, your efficiencies for a flat plate collector are higher. Whereas if your delta T values are higher than this delta T1 value at this crossover point, then your efficiency values for an evacuated tube collector is higher. So in this regime of operation, flat plate collectors are preferred, and in this regime of operation, evacuated tube collectors are preferred. Okay. And also because your resistance is higher, you have a much higher stagnation temperature for an evacuated tube collector compared to the flat plate collector. So your absorber plate and your heat transfer phase change fluid can be heated up to much higher temperatures compared to your flat plate collector absorber plate. Okay, that is why you can sustain higher temperatures, outlet temperatures for a heat transfer fluid. So if you want higher temperature values, you should prefer evacuated tube collectors, which can give reasonable efficiency even at higher outlet temperatures, where your flat plate collector will not work. And this is very useful if you think of in cold climates. So in winters, say in northern Europe or Canada, your ambient temperatures can go below freezing. It can be minus 20 degrees, minus 15 degrees centigrade. To get your hot water to say 70 degrees centigrade, which is kind of the minimum you would need for usual domestic applications, the temperature difference there will be TW out minus T ambient, which is 85 degrees. Okay, so this delta T would be around 85 degrees. Whereas in a warm climate, like in Indian climates usually, your ambient temperatures rarely go below freezing. It can be 4 degrees, 5 degrees C, and your hot water, the flat plate collector, can still go to 70 degrees, and the temperature difference between the ambient and the collector is 65 degrees only. So you have a 20 degree difference for usual working domestic applications there. So in some cases then, evacuated tube collectors is the better choice in colder climates compared to flat plate collectors. Okay. Now here we have used a very simple expression where your thermal resistance is given by one parameter R, okay, constant. Usually, however, the resistivity depends on the temperature gradient itself. So this temperature gradient delta T, the resistance R is not a constant but a function of this delta T. So we can often write 1 by RA on a, if you do a more detailed heat transfer analysis, as alpha 1 plus alpha 2 into delta T. Okay. So this kind of a function can be fitted if you do a more sophisticated heat transfer thermal resistivity applications. So if you put 1 by RA as alpha 1 plus alpha 2 into delta T, you will get this efficiency eta as 1 minus rho minus alpha 1 into delta T plus alpha 2 into delta T square by G0. So you have 1 by RA becomes alpha 1 plus alpha 2 delta T into delta T. So this becomes this expression here and it becomes G0. So now the efficiency becomes a quadratic function of delta T. Okay, so it becomes kind of this kind of a quadratic function. Okay. And if you look at the quadratic function, you will see that for flat plate collectors, the quadratic function is extremely steep, wherein for an evacuated tube collectors, the quadratic function is not as steep. So the actual region of operation of evacuated collectors is actually higher for more accurate quadratic evaluations than you will see in a linear evaluation. Okay. Another problem that comes is often you do not actually know the temperature of your absorber plate. So if you think of your original system like this system or like this system, how would you find the temperature of the absorber plate? You get the temperature of the inlet fluid and the outlet fluid using thermocouples, but the temperature of the absorber plate is not usually known. So this efficiency value, which depends on the temperature of the absorber plate minus ambient temperature, is difficult to use in practical systems. So what we do here is we take a mean fluid temperature. Mean fluid temperature is the outlet temperature of the heat transfer fluid plus inlet temperature of the heat transfer fluid by 2. Okay. So basically in this expression, T out plus T in by 2 is the mean fluid temperature. Okay. This we can evaluate directly using thermocouples. Then the efficiency eta can be rewritten as a function of two different efficiencies. One is eta PF, which is the efficiency of heat transfer between the plate and fluid. So what is the efficiency of heat transfer between this absorber plate and the fluid? That efficiency is eta PF into 1 minus rho minus, instead of delta T, we put the mean fluid temperature minus ambient temperature. The original delta T was absorber plate temperature minus ambient temperature. Here is mean fluid temperature minus ambient temperature by RAG0. Okay. This is said to be equal to this expression here. Okay. Eta PF into 1 minus rho minus mean fluid temperature minus ambient temperature by RAG0 is equal to 1 minus rho minus T plate minus T ambient by RAG0. Okay. So we have replaced the plate temperature by the mean fluid temperature and taken a efficiency of heat transfer between the plate and the fluid as a correcting factor. And this eta PF is of the order of 0.85. So we have seen some of the quantitative analysis studies. So now we will discuss some of the typical performances we get for different types of collectors. So the simplest type is a flat plate collector with a black absorbing plate and there is no glass cover. Okay. Then RPA is the resistance to heat losses through the top of the collector for a standard condition. You remember the resistance depends on delta T also. So standard condition is the plate temperature is 90 degrees centigrade, ambient temperature is 20 degrees centigrade, and the flow rate of wind, I think this is the wind flow rate, it may be the water flow rate also, it's not very necessary, is 5 meters per second because there is convection losses as well, correct? So a typical wind flow rate has to be also be given. So this is a standard set of conditions for which all these resistivities are evaluated, and resistivity is given is meter square per kilowatt. Okay, this is another way of evaluating this same expression. So you can see the resistivity here is 0.03, which is quite small, and the TPM is the stagnation temperature when the G0, the solar irradiance, is 750 watt per meter square. Okay. So the maximum stagnation temperature under this condition with ambient of 20 degrees is 40 degrees centigrade only. Okay. So for an unglazed collector without any glass cover, you are getting very low resistance, and hence your stagnation temperature is also quite low. And this is used for swimming pools as very cheap for hot water supply. Okay, this is otherwise not very much used. The most common is a black absorber plate with a single glazing. So you have a single glass plate at the top. Okay. You see the resistance has increased from 0.03 to 0.13, which is a significant improvement, and the stagnation temperature has increased to 96. Remember, the ambient temperature is 20 here. Okay, so your delta T is 96 minus 20, which is 76, correct? That is the delta TS. Okay, so you are getting a very good uptick in thermal resistance and a reasonably good stagnation temperature. So it's the cheapest and the most widely used version of flat plate collector. Okay. Then you have a double glazing. So instead of one glass plate, you have two closely stacked glass plates. So this kind of the space between the two glass plates have a very small spacing. So the conduction and convection are completely stopped. Okay. So this again improves the resistance further from 0.13 to 0.22. And hence increases stagnation temperature to 140. So now the delta T is 120. Okay, this is a small price increase, and you are getting a significantly higher operating temperature is possible now. Okay. Then you go into selectively coated absorber plating. So as we discussed, the absorber coat is usually black coat, but you can have a selective coating which absorbs the solar radiation but does not emit thermal radiation. Okay, so that also removes the radiation heat transfer losses. Okay, so if a selective coating with a single glazing is done, then your resistance increases to 0.4. See the significant increase now, and your stagnation temperature goes to 240. So now you can think of converting water to steam. Okay, so this is an important improvement, particularly for industrial applications at moderate extra cost. Okay. The selective coating with double glazing is not very useful because this effect takes into account this point directly. And finally, you have your evacuated tube collector where your circular absorber coating is also selective. Okay, so your absorber coat is selectively coated, so it absorbs the solar radiation but does not emit thermal radiation. Already you have evacuated tube, so convection, conduction, radiation, all three are minimized. Okay, and your resistance is around 0.4 again, and your stagnation temperature goes up to 300 degrees centigrade. Okay, so this is important for higher temperature but is more expensive. Okay. So those are the various types with their own efficiency factors. So now let us look at a few examples. So I will look at the worked out examples directly today because it's more useful when we are discussing the theory and the worked out examples together. So here we are considering a flat plate collector A having parameter rho A, the reflectivity as 0.362, and then the resistance parameters are alpha 1A as minus 4.26 and alpha 2A as minus 0.03. Okay, and we are comparing this with an evacuated tube collector with reflectivity of 0.689 and alpha 1B as minus 1.17 and alpha 2B as minus 0.01. Let's understand what these values are. We are using this value, alpha 1 plus alpha 2 delta T as 1 by Ra, and the values of alpha 1 and alpha 2 are given for a flat plate collector and an evacuated tube collector, as well as the resistance, the reflectivity values are also given. Find the temperature above which the evacuated tube collector has the superior efficiency for two cases. A location where the G0 value, the solar flux, is 1000 watt per meter square, and a location where the G0 value, the solar flux, is 250 watt per meter square. Okay. So here the efficiency is given by E in this problem. So eta of the flat plate collector, eta of the evacuated tube collector minus eta of the flat plate collector is 0. That is the point where you have the crossover case, right? So where the two efficiencies are the same. So eta of the flat plate minus eta of the evacuated plate are the same. So this becomes 0 is equal to rho A minus rho B, the difference in the reflectivities, plus alpha 1A minus alpha 1B delta T by G0 plus alpha 2A alpha 2B delta T square by G0. Okay. Now we put G0 as 1000 and put these values of alpha 1 and alpha 2, and we get delta T as 453 degrees centigrade. So if the delta T is below 453, then you should use a evacuated flat plate collector, and if delta T is greater than 453, then you should use a evacuated tube collector according to this problem for a solar flux of 1000 watt per meter square. Now look at a location where the solar flux is 250 watt per meter square. Again, you solve the same quadratic, the values of G0 are different, and here the delta T is 355 degrees centigrade. So here the delta T has decreased, so you will use the evacuated tube collector whenever your delta T is higher than 355 degrees centigrade, and use the flat plate collector whenever your delta T is lower than 355 degrees centigrade. Okay. We will look at another example problem. Here we have a flat plate collector measuring 2 meter cross 0.8 meters. So the length is 2 meters and the breadth is 0.8 meters. The resistance, the thermal resistance is 0.13 Kelvin meter square per watt. Okay. 0.13 Kelvin meter square per watt. This is the unit of your resistance, and the efficiency of your of the plate to fluid efficiency. So this expression here, eta PF here, is given as 0.85. Okay. The net transmittance is 0.81. Transmittance is 1 minus the reflectance. Okay. The inlet temperature of a fluid is 40 degrees. The ambient temperature is 20 degrees, and the solar flux G0 is 750 watt per meter square. We have to find the flow rate in liters per hour that can be sustained when we need outlet water temperature of 80 degrees centigrade. So the inlet water temperature is 40 degrees. We want an outlet water temperature of 80 degrees. The ambient temperature is 20 degrees. The solar flux is 750 watt per meter square. The plate to fluid heat transfer efficiency is 0.85. The collector area is 2 cross 0.8. Collector resistance is 0.13. These are the values we know. The reflectivity is 0.81, so 1 minus rho is 0.81. Okay. And the heat that is being absorbed by your fluid is efficiency into the heat that is being incident on your solar flux. Okay. The incident solar flux, which is G0, which is equals to the mass flow rate into the specific heat into T out minus T in. Okay. So this way, if you know the heat that is being absorbed by your fluid, and you know the T out and T in values, you know the specific heat, it is of water, you can evaluate the mass flow rate m dot using this expression. So the first task is to find the heat that is being actually absorbed by your fluid. This is given by the efficiency eta, which is equals to eta PF into 1 minus rho minus the mean fluid temperature minus ambient temperature by RAG0. The mean fluid temperature is 80 plus 40 by 2 is 6 degrees centigrade. 80 plus 40 by 2, 6 degrees centigrade. Ambient is 20. So you know all these values. Rho, this is 0.81. R is given as 0.13. A is basically 2 into 0.8. So 1.6. G0 is 750. So you put these values and you get eta as 0.47. So the Q dot absorbed is eta into Q dot incident, which is eta G0 into A. G0 is 750, A is 1.6, eta is 0.47. Put those values there. It becomes 564.44 watts. Okay. So this Q dot absorbed is 564.44. The specific heat of water is 4.18 into the power 3. Density of water is 1000. So Q dot absorbed is this expression here, 564. The density of water into volume flow rate of water into specific heat into 80 minus 40. You get all these values. So the volume flow rate of water becomes 3.377 into 10 to the power minus 6 meter cube per second. Convert into liters per hour, it becomes 12.16 liters per hour. So you can flow around 12 liters per hour of fluid through the system at the operating conditions to get an outlet temperature of 80 degrees. Okay. So that's how you solve these kinds of problems. So today I will stop here. In the next class, we will discuss the last type of solar thermal systems where you are using the thermal energy of the sun to generate electricity through what is called the concentrated solar thermal power, CSP technique. Okay, we will discuss that in the next class. Thank you for listening, and we will meet you next time.